Hello everyone. This is the second part of the series on bounded sets in Rn. So in the first part of this series, which is linked down in the description below, we discussed the definition of Rn and we defined bounded sets in Rn. And we in particular paid attention to how the definition of bounded sets in Rn is analogous to the definition of bounded sets in R. So in this video, we are going to recall what is the definition of a bounded set in Rn, and we're going to focus on examples of bounded sets in Rn. So in particular, we'll look at balls in Rn. We will define what is a ball. We will look at finite unions of balls, and we will prove that those are bounded sets. And finally, we will consider an example of a set that is defined in such a way that we can't quite depict it. So it's defined in terms of basically mathematical symbols. And nevertheless, we will prove that that set is bounded. And that example is something that you may encounter in proofs of other theorems as a step. So it's very worthwhile to see it. So I hope you'll enjoy it in this video. So let's go ahead and recall the definition of a bounded set in Rn. So a set S that is a subset of Rn is bounded if there exists a positive number B such that whenever we take an element X of the set S, the norm of that element is always going to be less than or equal to this positive number B. So this is a formal definition. Let us look at an illustration to develop an intuitive understanding of what this means. So here basically we see the plane R2, and in the yellow color you see the set S. So let's just assume for a moment that the set S is here in this yellow color. So I claim here that the set S is bounded, and I'm going to try to convince you why it is so. So if I take an element X in S, do you guys remember the geometric meaning of the norm of the element X from the previous video? So in case you didn't watch the previous video, or in case you've forgotten, this meaning is that the norm of X is the distance from X to 0. So the length of this segment over here is the norm of X. So the norm of X is the distance from X to 0. And so I would like to convince you that it doesn't matter what X I take inside of the set S. So I can denote this as x1, and this is x2, and this is x3. So no matter what element in the set S I take, whether it be x1, x2, or x3, or any other element, the distance from that element to 0 is going to be bounded by some number that is predetermined. So let me just draw here a circle of radius b. So let's just say that this is positive number b, and I'm going to draw a circle of radius b. So from this picture, you see that obviously the set S is inside of this circle. But what does that mean? It means that if I take an element X inside of the set S, the distance from X to 0 is going to be less than the radius of this circle, which is the number b. Right? So for every X in S, the norm of X, which is distance from X to 0, is less than or equal to this number b, which is the radius of this circle. So this is a way to help us to understand more intuitively what it means for a set to be bounded in Rn. And so you can imagine that if you were in R3, right? So if you were in R3 and you had a set that is three-dimensional, right? So something weird looking like this, if that set is inside of a ball, of some finite radius b, then the set S is bounded, okay? So we can generalize this notion. We can define a ball in Rn, and it actually is true that if a set is inside of a ball in Rn, then it is bounded. So it's another way to look at bounded sets. So let us now define the n-dimensional ball of radius r centered at the point y in Rn. So it's actually going to be this set. It's the set of all points in Rn such that the distance from these points to the point y is less than r. Okay, so because this norm of x minus y is actually the distance between the points x and y. So let us illustrate this on the example of R2. So by the way, I'm just gonna denote the coordinates by x1 and x2. So in my previous picture, I denoted them as x and y, and it's not wrong, but just to be consistent, let us keep denoting them as x1 and x2, just to be consistent with the notation of the previous video. So in any case, so we have here the example of R2, and let's just assume that the point y in R2 is here, and that r is the radius. So let's just assume that the length of this segment over here is r. So the ball centered at y of radius r is going to be this disk. So not just this circle, not just the boundary, but everything that's inside this disk. However, what do you guys think? Is the boundary included or not? Because this inequality is strictly less than r. So this set BYR, it contains all of the points x such that the distance from x to y is strictly less than r. So if I'm on the boundary, if I take a point, say x2 on the boundary, and I look at the distance from x2 to y, the distance is going to be exactly r. However, the definition of the set BYR tells us that this point should not be in the set B. So the set B is actually this everything that's inside this circle. So everything that's inside this disk, but it is not the boundary. So in complex analysis, we would call this set an open disk. Okay, and so this ball is called an open ball. And the reason why it's called open is because the boundary of the ball is not included in the set. And so what we intuitively understood in an example that we looked at before is that if we take a set in Rn, it is going to be bounded if and only if there is some ball in Rn that contains the set. And so of course the y is a point in Rn and r is a finite positive number. So let's just illustrate this statement. So suppose we are dealing with R2. So we are on the plane. And we have a set that looks like this. So everything inside this rectangle is in the set. Now the question is the set S bounded or not? What do you guys think? So if you thought that it was bounded, then you were right, because we can definitely draw a finite, because we can definitely draw a circle of finite radius that contains this set S. So it's gonna be a ball centered at some point y of radius r. So the set S is definitely contained in the ball centered at Y of radius R. So the set S is bounded. So in this example, the set S is actually an open strip. So it's everything in between these two straight lines that are dashed. So everything in between this line right here and this other line over here. So everything in between these two lines, not including these two lines, is in the set S. Right? And it keeps going on forever up and it keeps going on forever down. So what do you guys think? Is this set bounded or not? So if you thought that the set was not bounded, you were correct. And this is because it doesn't matter how big of a circle we draw around this set, there will always be a portion of the set S that is outside of the disk, right? So I'm drawing here, this is a portion of the set S that is outside of the particular disk that I have drawn. And so this is why the set S is not bounded. So this example is about the union of M balls in Rn. So we have M points in Rn and we also have M positive numbers. And so if we take Y1, that can be the center of the first ball, and R1 is the radius of the first ball. Then we can take Y2 to be the center of the second ball, R2 is the radius of the second ball, and so on. And we can finish at Ym and Rm. So we get the idea. So we have M balls, and if we take a union of all of these balls and we form a set S, so it turns out that the set S is bounded. So let's just think about this intuitively. We're just going to illustrate this without really doing a rigorous proof. We're going to focus on intuitive understanding here. So suppose I have a ball centered at Y1 of radius R1. And then I have another ball centered at Y2 of radius R2. And then I have another ball of centered at Y3 of radius R3. And then I have another ball centered at Y4 of radius R4. You get the idea, right? And then a bunch of balls, and then let's just say that the last ball is centered at Ym of the radius Rm. Then the set S is going to contain all of these balls. Yes, and there are some balls that we didn't draw, so the set S is going to contain all of them. And of course, because there are finitely many balls, so even if there were 100 balls or 1 million, there are finitely many balls, so it is clear that you can figure out some big radius and some center and draw a huge ball in such a way that it contains all of the balls that form the union that is your set, right? So this set that is the union of all of the balls is clearly bounded. Let us consider another example. So let yk be a sequence in Rn that is bounded. So every term of the sequence yk is an element of Rn, and this sequence is bounded. Let Rk be a sequence of positive numbers, so every term of the sequence Rk is a positive number, and assume that this sequence is bounded. Now let us look at this set, which is the union of all of the balls that are centered at yk and have radius rk. We want to show that this set S is bounded. So let us begin with trying to understand what is going on here. Let us begin with some scratch. So just like in the previous example, let us consider the case of R2. So what we have in here is that we have a sequence of points in R2 that are denoted as y1, y2, y3, and so on. So we have an entire sequence, yk, and each yk is in R2 for every k natural number. So we are looking at the case of R2. Of course, our example is the case of Rn, but we are just looking at the case of R2 so that we can understand what's going on. So we have a sequence yk that is bounded. It means that there is a number m, some positive number, such that the norm of yk is less than or equal to m for every k natural number. So that means that all of these elements yk are actually inside of the circle of radius m, right? So there is some big circle of radius m centered at 0, right? So the radius is m. All of these points, y1, y2, y3, and so on, they are inside of this big circle. So let us denote this disk centered at 0 of radius m as b0m. Okay, so I'm using here the letter b and not d because just to be consistent with the notation for balls. So this is a ball centered at 0 of radius m. So for every k natural number, yk is inside of this ball centered at 0 of radius m. So now let us try to understand what is this set S. So the set S is built with these building blocks that are balls centered at yk of radius rk. So around the point y1, let us draw the ball of radius r1. So in the case of R2, it's just going to be a disk of radius R1. Then around the point Y2, we can draw the disk of radius R2. Around Y3, the disk of radius R3, and so on. And so if we take a union of all of these balls, and there are infinitely many of them, so if we take a union of all of these balls, we are going to get the set S. Now, what we want to show that S is bounded. So we want to show that there exists a ball such that S is inside that ball. So what is important here is that the sequence Rk is bounded. So let us make sure that we utilize that. So it means that there exists a positive number r such that the absolute value of Rk is less than or equal to r for all k's. So this is important, and why would that be important? So we know that all of the points yk are inside of this ball b centered at 0 of radius m, right? So there will be no situation where one of these points ym is outside of the ball, right? Because they're all inside, so that is not gonna happen. They may be on the boundaries though. Now we can formulate the question, is it true that the set S is inside of this ball B0M? So the ball, which is the disk in this case, centered at 0 of radius M. So it would be not true to say that the set S is inside of this ball. And here is the reason. So it is possible to have an element of the sequence yk such that it is on the boundary of the ball B0M. And so the disk centered at ym of radius Rm is going to be part of the set S. So the ball centered at ym of radius rm belongs to the set S, right? So hypothetically this is possible, and so we can see why we cannot say that the set S is inside of this ball. However, what we know is that absolute value of Rm is less than R, and so if we take the ball B of radius m plus R, we should be able to account for all of these situations, right? So if we look at the ball centered at 0 of radius m plus R, so where R would be this portion over here, right? And R is going to be larger than the radius of this ball centered at ym. So we know that the set S, so claim is that the set S is going to be inside of the ball B centered at 0 of radius m plus R. So if we prove this claim, we will show that the set S is bounded. And that is the end of Scratch. So let us now get rid of the Scratch and write a clean proof of the statement that the set S is bounded. So as we mentioned before, the sequence yk is bounded, so therefore there exists a positive number m such that the norm of yk is less than or equal to m for all k in n. And similarly for the sequence rk, there is a positive number r such that the norm of rk, which is, by the way, its absolute value of rk, is less than or equal to r for all k. So as we mentioned in the Scratch and from what we saw from the picture, we want to show that the set S is inside of the ball B centered at 0 of radius m plus R. So in order to show this, we need to take a point x in the set S, and we are going to have to show that x is in this ball B centered at 0 of radius m plus R. So all we need to show is that the norm of x is less than or equal to m plus R. Now, S is a union of all of these balls, right? So if x belongs to S, it has to belong to one of these balls, right? So there exists m natural number such that x is in the ball B centered at ym of radius rm, right? So this is just a simple restatement of the fact that because S is a union of all of these balls, and because x is in this union, x has to be in one of the balls. But if we just write down the definition of what this means, this implies that the norm of x minus ym is less than or equal to rm. However, the rm is less than or equal to capital R. So this is less than or equal to capital R. But we need to show that the norm of x is less than or equal to m plus r. So we are going to write down the norm of x, and somehow we want to use this fact here, right? So what we are going to do is that we are going to write the norm of x as the norm of x minus ym plus ym. And then we are going to use the triangle inequality. So this is less than or equal to norm of x minus ym plus the norm of ym. So as far as this portion is concerned, this is less than or equal to capital R. And then ym, we know that is less than or equal to capital M. So altogether, this is less than or equal to capital M plus capital R, just as we wanted to show. So this means that we proved the claim. So we proved the claim. And now, because the set S is contained in a ball of finite radius, so by the previous proposition, S is bounded. And that finishes the proof. Okay, so I hope it was helpful for us to see intuitively how to prove that sets are bounded. This last example was a little bit more advanced. However, we were able to handle it just fine with developing some intuitive understanding of what is going on, drawing a picture, doing some scratch, and after that we were able to show that the set S is bounded. So this is all for this video. I hope that you enjoyed it. Please give it thumbs up. Please support this work and be good at math.